So today we are talking about the side-splitting theorem, and this follows pretty directly from what we've been talking about with similar triangles. Here's what the side-splitting theorem says. If two sides of a triangle are split with a line that is parallel to the third side, the segments created are proportional. So that's probably hard to follow just reading it, but what that means is if you've got this triangle here, and I take this line and I cut through two of the sides of the triangle so that this line here is parallel to this third side. Let's mark that real quick. So this is parallel to this. Then the smaller segments, meaning like X and W and Y and Z, are proportional. So I could use this to write a proportion, almost just the way it's set up right now. I could say X over W is equal to Y over Z. And this is new because we have never dealt with these segments as individual pieces. We have done problems where we've been talking about like this short side and then this whole side, but we've never looked at this piece as compared to this piece. Okay? The thing I want to caution you about here is this trick with the proportion, this trick with the proportion here only works with these split sides. Okay, you cannot compare these two pieces like Y and Z to these sides, the parallel line and then the bottom of the triangle. You'll see what I mean by that when we do our first example, okay, but you may just want to make a note of that to yourself. So let's take a look at this example. This is example 1 in your notes, and you can see that we have a triangle here, okay, that has been split with that line so that it's parallel with this line down here. So this is the exact situation that the side-splitting theorem is talking about. And what that tells us is that these little pieces that are formed are proportional. Okay? So I want to find Rn, which is this side length here. I'm going to mark that with an X. And since that's one of my split sides, I can set up a proportion with these four numbers and then solve. So I would say X over 120 is equal to 140 over 80. And then I would just solve like you solve any other proportion. So I would do 120 times 140 is 16,800. And that's going to equal 80 times X. Okay. And I would divide by 80, and for a final answer I end up with X equals 210. So the length of Rn is 210. Now the next one wants you to find the length of TS, which is this side down here at the bottom. And this is what I was talking about on that last slide when I said that this only works with the split sides. This side that I'm looking for is not a split side. It does correspond with this 168. They are going to be proportional. But when I go to compare this, let's call this one Y. When I go to compare the Y and the 168, I need to compare those with the large side and the short side of the triangles themselves, not the split sides. So let's set up the first part of that proportion. I know Y goes with 168. And again, because these are not split pieces, I have to think of these as sides of a big triangle and sides of a small triangle. So the Y is from the big triangle, and the 168 is from the small triangle. So I'm going to set that equal to another set of side lengths from the big and the small triangle. And remember, today we talked about how I always try to use the numbers that the problem gave me originally, not a number I calculated, because I may have made a mistake. So I'm going to use this set of side lengths right here, but when I say I want the big side length, I need this entire side length. So that would be 140 plus 80 is 210. So it goes here. And then the small side length that goes along with that 210 is the 140. Okay. So the 210 is the side length in this big triangle. The 140 is the side length in the small triangle. Okay, to correspond. So 140 goes with 168 and 210 goes with y. Now I'm going to solve this like a proportion too. So I'm going to go 210 times 168 is 35,280. And that will equal y times 140. Then divide by 140. Divide by 140. And I end up with y equals 252. Okay. So again, when you're looking at the sides that are not being split by that parallel line, you have to use the entire side length, not just the pieces. You have to use the entire side length with the short side length. Okay, we'll do some more practice with that in class for sure. Okay, the converse of the side-splitting theorem is also true. So the regular side-splitting theorem says that if you have this line that's parallel in a triangle, then it creates sides that are proportional, or split sides that are proportional. Notice that this one, the converse, says if the sides form, if you split it and the segments are proportional, then you know they're parallel. So the old one said if you know it's parallel, then they're proportional. This says if they're proportional, then you know they're parallel. I'm not going to spend a lot of time having you, I don't want you to spend a lot of time thinking about the difference between the converse of the side-splitting theorem and the regular side-splitting theorem. I just want you to know that it works both ways. So what this is really saying is if I have a triangle and I draw this line right through the middle, maybe not through the middle, but I draw it so that these side lengths come out proportional. Okay, so let's say, I don't know, maybe this is going to be 9, and this is 6. Well, my k value to get from 9 to 6 is 2/3, because 9 times 2/3 is 6. So if I had this be 12, and I multiplied by 2/3, that would be 8. So if I set these up to be proportion, 9 over 6 is proportional with 12 over 8. Okay, so I kind of made up those numbers on the fly. I wanted you to see how I was doing it. That's why I was showing you this. But since these numbers would form a true proportion, we know these side lengths are proportional. I could also think of it as 9 times 8 is equal to 12 times 6. Remember, that's how you check a proportion. Once you know that they're proportional, that lets you conclude that this line that we drew is parallel to this one. Okay, so it's the same idea. It's once you know they're proportional, then you can say the sides are parallel. Last example here. It wants to know, are these lines parallel? Which, to be honest, I didn't realize this until now that they're already marked as being parallel, but we probably should ignore that. Okay, pretend that's not there. There we go. Okay, so the way I would check to see if they're parallel is I would check to see if these numbers and these numbers form a true proportion. So I would say 12 over 3, and I want to know, is that equal to 8 over 2? Well, you could divide them both separately. You could say 12 divided by 3 is 4, 8 divided by 2 is 4, so yes, this works. Or you could cross multiply. 12 times 2 is 24, 8 times 3 is 24, so since they're equal to each other, they are proportional. So my answer, I would say something along the lines of, yes, because the split sides are proportional. So I would check those numbers, make sure they form a proportion. Now that I know that they're parallel, I'll go ahead and draw those back in. Okay? That's it for the side-splitting theorem. Tomorrow in class we'll spend some time practicing with this, and then hopefully you'll be able to get away without a homework assignment this weekend. Please email me if you have any questions or technical difficulties or anything like that. Thanks a lot.